Yobagi Bayaw. Today I'm going to show how to solve a problem in Thermodynamics, Chapter 7, Refrigeration Cycle. So this is my problem. You can see this problem from the book of Eunice A. Single Manual, Problem 11-55. An ideal gas refrigeration cycle with air as the working fluid is considered. The maximum and minimum temperature in the cycle, the COP, and the rate of refrigeration are to be determined. So we are looking for the maximum and minimum temperature and the COP and rate of refrigeration. So for our assumption is steady operating condition exists. Air is an ideal gas with variable specific heats, and kinetic and potential and energy changes are negligible. To analyze it, we assume both the turbine and the compressor to be isentropic, the turbine inlet temperature to be the temperature of the surrounding, and the compressor inlet temperature to be the temperature of refrigerated space. From the air table, we have table A-17. So our temperature 1, we have two temperature 1, which is 250 Kelvin and 300 Kelvin. So we're going to find their P sub R1 and enthalpy sub 1 and P sub R3 and enthalpy 3. So for 250, we have PR sub 1 is equal to 0.7329 and enthalpy 1, which is 250.05 kilojoule per kilogram, and PR sub 3 is equal to 1.386 and enthalpy 3, which is equal to 300.19 kilojoule per kilogram. Then after that, we're going to find the maximum and minimum temperature. For the equation that we're going to use to get the maximum temperature, we have P sub R2 is equal to pressure 2 over pressure 1 times PR sub R1. So we have 3 times 0.7329. Our P sub R2 is 2.1987. Then after that, we're going to find the temperature maximum and enthalpy sub 2. So temperature 2 is equal to temperature maximum is equal to 342.2 Kelvin. Then our H sub 2 is equal to 342.60 kilojoule per kilogram. Then after that, we're going to find the pressure P sub R4 rather to get the temperature minimum. The equation that we're going to use is same from the equation above, but we're going to change the P sub R1 to P sub R3. So our value is 1 over 3 times 1.386. Our P sub R4 is 0.462. To get the minimum temperature, we have T sub 4 is equal to T min is equal to 219.0 Kelvin. And we have also enthalpy 4, which is 218.97 kilojoule per kilogram. Then after that, we're going to find the COP or coefficient or COP of this ideal gas refrigeration cycle is to determine from the equation of COP refrigeration is equal to QL over work net in. So other equation for that is QL over work compressor in minus work turbine out. After that, we're going to find first the QL, which is the equation is enthalpy 1 minus enthalpy 4. Since we already have enthalpy 1 and enthalpy 4, we're going to substitute it, or we're going to put the given. So 250.05 minus 218.19 kilojoule per kilogram. Our QL is Q sub L rather is 31.08 kilojoule per kilogram. Then after that, we're going to look for work compressor in. So the equation for that is enthalpy 2 minus enthalpy 1. So we're going to solve it. Our work compressor in is 342.60 minus 250.05 To calculate it, we have 92.55 kilojoule per kilogram. Then after that, we're going to find the work turbine out, which is the equation is enthalpy 3 minus enthalpy 4. So 300.09 minus 218.97 kilojoule per kilogram, we have 82.22 kilojoule per kilogram. Since we already have the Q sub L, or specific heat Q sub L, and work compressor in and work turbine out, we're going to compute the COP of refrigerator. So our Q sub L, which is 31 kilojoule per kilogram over 92.55, which is work compressor in minus the work turbine out, which is 81.22 kilojoule per kilogram. Our COP refrigerator is 2.74. After that, we're going to look the rate of refrigeration. The equation for that is Q, or there's a point above the Q. So Q refrigerator is equal to per unit time. Q refrigerator per unit time is equal to mass per unit time times Q sub L. So we have 0.08 kilogram per second times 31.08 kilojoule per kilogram. Our Q sub refrigerator per unit time is 2.49 kilojoule per second. Thank you for listening and watching, and have a great day.